To effectively ground multiple electrical services to a water line, several steps must be taken to ensure safety and code compliance. The following will explain the procedure in detail. Firstly, prepare the grounding system. This involves installing an 8-foot copper-clad ground rod near the water service entrance. The purpose of this ground rod is to provide a supplemental grounding electrode to help stabilize the electrical potential and provide a path for fault current to return to the source. It is crucial that the ground rod is made of copper-clad steel to resist corrosion and provide good electrical conductivity. After installing the ground rod, connect it to the cold water pipe using a ground clamp and wire. The ground clamp should be made of a material compatible with both the copper ground wire and the water pipe material to prevent galvanic corrosion. Use a suitable size copper wire, typically a 6 AWG or larger, to make this connection. This connection establishes a direct electrical bond between the ground rod and the water pipe, enhancing the overall grounding system. Secondly, connect the main panels. This is done by using a 4 AWG bare copper wire to connect the ground bars of all 8 electrical panels to the cold water pipe within 5 feet of the entrance. The 4 AWG wire size is specified to handle the potential fault current from multiple services. The connection point in the cold water pipe must be within 5 feet of where the pipe enters the building to comply with electrical codes and to minimize impedance. Ensure all connections are tight and weatherproof. This is essential to prevent corrosion and maintain a low-resistance grounding path. Use appropriate connectors and apply a corrosion inhibitor to the connections. Thirdly, connect the house panel. Follow the same procedure as in step 2 to connect the house panel to the cold water pipe. This ensures that the house panel is also properly grounded and bonded to the main grounding system. Use a 4 AWG bare copper wire to connect the ground bar of the house panel to the cold water pipe within 5 feet of the entrance. Again, ensure that all connections are tight and weatherproof. Fourthly, connect the house meter. Connect a 4 AWG bare copper wire from the ground bar of the house meter to the cold water pipe. The house meter needs to be grounded to ensure that any fault current can safely return to the source. Use a suitable connector to make this connection and ensure that it is protected from corrosion. Fifthly, install a grounding plaque. Install a grounding plaque on the inside of the apartment building near the water service entrance. The grounding plaque serves as a central connection point for all the grounding conductors. This makes it easier to inspect and maintain the grounding system. Connect the plaque to the cold water pipe using a ground clamp and wire. Sixthly, connect the ground wires. Connect all 9 ground wires, 8 from the electrical panels and 1 from the house meter to the grounding plaque. This centralizes the grounding connections, providing a single point for inspection and maintenance. Ensure all connections are tight and weatherproof. Use appropriate connectors, such as compression connectors or split bolt connectors, to make these connections. Apply a corrosion inhibitor to protect the connections from moisture and corrosion. Additional tips to consider. Use a grounding wire with a minimum size of 4 AWG for connecting the panels and meter to the water pipe and grounding plaque. This wire size is typically required for multiple services to ensure adequate current carrying capacity for fault currents. Ensure that the copper-clad ground rod is at least 8 feet long and driven into the earth below the frost line. The 8-foot length is a standard requirement to ensure good contact with the earth. Driving the rod below the frost line helps to prevent movement due to freezing and thawing of the soil. Inspect the grounding system regularly to ensure proper connections and functionality. Regular inspections can help identify any loose connections, corrosion, or other issues that could compromise the effectiveness of the grounding system. Correct any problems promptly to maintain a safe and reliable electrical system. It is also very important to understand the requirements of the National Electrical Code, or NEC, regarding grounding and bonding. Article 250 of the NEC covers grounding and bonding requirements, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for bonding metal parts. Compliance with the NEC is essential for ensuring a safe and code-compliant electrical installation. Specifically, NEC Section 250.50 covers the grounding electrode system. This section requires that all grounding electrodes that are present at each building or structure served be bonded together to form the grounding electrode system. This includes metal underground water pipes, ground rods, and other grounding electrodes. NEC section 250.52 covers grounding electrodes. This section specifies the types of electrodes that can be used for grounding, including metal underground water pipes, ground rods, ground plates, and other types of electrodes. NEC section 250.66 covers the size of the grounding electrode conductor. This section specifies the minimum size of the conductor used to connect the grounding electrode to the service equipment. The size of the conductor is based on the size of the service entrance conductors. In addition to the grounding electrode system, bonding is also an important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a low impedance path for fault current to return to the source. This helps to prevent voltage differences between metal parts, which can be a shock hazard. NEC section 250.92 covers the bonding of metal parts. This section requires that all metal parts of the electrical system that are likely to become energized be bonded together. This includes metal conduits, metal enclosures, metal water pipes, and other metal parts. NEC section 250.104 covers the bonding of metal water piping systems. This section requires that metal water piping systems be bonded to the service equipment to ensure that they are at the same electrical potential. This helps to prevent shock hazards from contact with metal water pipes. Another critical aspect is the selection of appropriate connectors and hardware for grounding and bonding. Use connectors and hardware that are listed for grounding and bonding and that are compatible with the materials being connected. For example, use copper connectors for copper conductors and aluminum connectors for aluminum conductors. Avoid mixing different metals as this can lead to corrosion. Use corrosion inhibitors to protect connections from moisture and corrosion. Apply a corrosion inhibitor to all connections to prevent corrosion and maintain a low resistance connection. Inspect connections regularly for signs of corrosion and reapply the corrosion inhibitor as needed. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, which helps to trip the circuit breaker or fuse and to energize the circuit. Bonding connects all metal parts of the electrical system together to create a low impedance path for fault current, which helps to prevent voltage differences and shock hazards. Regular inspection and maintenance of the grounding and bonding system are essential for ensuring continued safety. Inspect connections for tightness and corrosion. Check the condition of grounding conductors and electrodes. Replace any damaged or corroded components. Test the grounding system to verify its effectiveness. A ground resistance meter can be used to measure the resistance of the grounding system. The resistance should be low enough to provide an effective path for fault current. If the resistance is too high, the grounding system may not be effective and could pose a safety hazard. Furthermore, it's important to understand the role of the equipment grounding conductor. The equipment grounding conductor, or EG, is a conductor that connects the metal parts of electrical equipment to the grounding system. The EGC provides a low impedance path for fault current to return to the source, which helps to trip the circuit breaker or fuse and to energize the circuit. The EGC is typically a green or bare copper wire. NEC section 250.118 covers the types of equipment grounding conductors. This section specifies the types of conductors that can be used as equipment grounding conductors, including copper wire, aluminum wire, and metal raceways. NEC section 250.122 covers the size of equipment grounding conductors. This section specifies the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device protecting the circuit. Additionally, consider surge protection. Surge protection devices, or SPDs, are devices that protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. SPD divert the surge current to ground, which helps to protect the equipment from damage. SPD should be installed at the service entrance and at any sensitive electronic equipment. NEC Section 230.8 covers surge protection. This section requires that surge protection be provided for all dwelling units. In summary, grounding multiple electrical services to a water line requires careful planning and execution to ensure safety and code compliance. By following the steps outlined above and adhering to the requirements of the NEC, it is possible to create a safe and reliable electrical system. Remember to always consult with a qualified electrician for any electrical work. The 4 AWG copper wire is a common minimum size for grounding electrodes, however, it could be larger based on a variety of factors. Review NEC Table 250.66 to verify the minimum size required for the application. This table cross-references the size of the service entrance conductors to the minimum size of the grounding electrode conductor. For example, if the service entrance conductors are larger than 1100 kcmil copper or 1750 kcmil aluminum, the grounding electrode conductor must be at least a 3/0 AWG copper or 250 kcmil aluminum. Also, NEC Section 250.64 discusses grounding electrode conductor installation. It requires the grounding electrode conductor to be installed in a continuous length without splices or joints, unless it is spliced by reversible compression-type connectors listed for the purpose, or by the exothermic welding process. The grounding electrode conductor must also be protected from physical damage. Where the grounding electrode conductor is exposed to physical damage, it must be enclosed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, or cable armor. The enclosure must be securely fastened to the surface on which it is mounted and must be protected from corrosion. When connecting to a metallic water pipe, the connection must be made within 5 feet of the point where the water pipe enters the building. This is to ensure that the connection is made to a section of the water pipe that is in direct contact with the earth. The connection must also be accessible for inspection and testing. The grounding electrode conductor must be connected to the water pipe by means of a listed grounding clamp or fitting. The clamp or fitting must be made of a material that is compatible with both the grounding electrode conductor and the water pipe. The clamp or fitting must also be securely fastened to the water pipe. When connecting to a ground rod, the grounding electrode conductor must be connected to the ground rod by means of a listed grounding clamp or fitting. The clamp or fitting must be made of a material that is compatible with both the grounding electrode conductor and the ground rod. The clamp or fitting must also be securely fastened to the ground rod. The ground rod must be driven into the earth to a depth of at least 8 feet. The top of the ground rod must be below the surface of the earth. If the ground rod cannot be driven to a depth of at least 8 feet, 2 or more ground rods must be installed. The ground rods must be spaced at least 6 feet apart. When connecting to a building steel, the grounding electrode conductor must be connected to the building steel by means of a listed grounding clamp or fitting. The clamp or fitting must be made of a material that is compatible with both the grounding electrode conductor and the building steel. The clamp or fitting must also be securely fastened to the building steel. The building steel must be in direct contact with the earth. If the building steel is not in direct contact with the earth, it must be supplemented by a ground rod or other grounding electrode. Also remember that the NEC is updated every 3 years and local codes may vary. Always consult the latest edition of the NEC and local codes for specific requirements in the area. Staying up to date with code changes helps ensure that electrical installations are safe and compliant. Another important consideration is the inspection and testing of the grounding system. After the grounding system has been installed, it should be inspected and tested to verify that it is properly installed and functioning correctly. The inspection should include a visual examination of all connections, conductors, and electrodes. The testing should include a ground resistance test to measure the resistance of the grounding system. The ground resistance should be low enough to provide an effective path for fault current. The testing should also include a continuity test to verify that all metal parts of the electrical system are properly bonded together. If the inspection or testing reveals any problems, the problems should be corrected before the electrical system is put into service. Regular inspections and testing of the grounding system should be performed to ensure that it remains effective over time. Proper documentation of the grounding system is also essential. Keep records of the installation, inspection, and testing of the grounding system. This documentation can be helpful for troubleshooting problems and for demonstrating compliance with the NEC and local codes. The documentation should include the size and type of grounding conductors, the location of grounding electrodes, the methods for bonding metal parts, and the results of ground resistance tests and continuity tests. In addition to the technical aspects of grounding, it is also important to consider the human factors. Electrical work can be dangerous, and it is essential to take precautions to protect yourself from electrical shock. Always de-energize circuits before working on them. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working on electrical systems, hire a qualified electrician. Safety should always be the top priority. Proper training and education are essential for anyone working on electrical systems. Take courses and seminars to learn about the NEC, grounding and bonding, and other aspects of electrical safety. Stay up to date with the latest information and best practices. Continuous learning can help prevent accidents and ensure that electrical work is performed safely and correctly. Remember that grounding is not a substitute for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Grounding provides a path for fault current to return to the source, which helps to trip the overcurrent protection device and de-energize the circuit. Overcurrent protection devices should be properly sized and installed to protect the electrical system from damage. In conclusion, grounding multiple electrical services to a water line involves a series of carefully executed steps, adherence to the National Electrical Code, and a commitment to safety. By following these guidelines, you can ensure a safe and reliable electrical system that protects people and property from electrical hazards. Always consult with a qualified electrician for any electrical work to ensure that it is performed safely and correctly. Furthermore, it is essential to understand the specific requirements of the local electrical codes and regulations. Local codes may have additional requirements or variations from the NEC that must be followed. Contact the local electrical inspection authority to obtain information about the local codes and regulations. Compliance with local codes is essential for ensuring that electrical installations are safe and legal. The local electrical inspection authority can also provide guidance and assistance with electrical inspections and permitting. Working closely with the local electrical inspection authority can help ensure that electrical work is performed correctly and that the electrical system is safe and compliant. When performing electrical work, it is important to use the correct tools and equipment. Using the wrong tools or equipment can be dangerous and can lead to accidents or injuries. Use insulated tools that are designed for electrical work. Use a multimeter to measure voltage and current. Use a ground resistance meter to measure the resistance of the grounding system. Use a wire stripper to strip insulation from wires. Use a crimping tool to crimp connectors onto wires. Use a conduit bender to bend conduit. Using the correct tools and equipment can make electrical work easier, safer, and more efficient. Proper maintenance of electrical tools and equipment is also essential. Keep tools clean and dry. Inspect tools regularly for damage. Replace any damaged tools. Store tools in a safe place. Proper maintenance of electrical tools and equipment can help prevent accidents and ensure that the tools are always ready to use. In addition to the technical aspects of grounding and bonding, it is also important to consider the aesthetic aspects. Electrical installations should be neat, clean, and professional looking. Wires and cables should be properly supported and routed. Connections should be tight and secure. Equipment should be properly labeled. A well-organized and aesthetically pleasing electrical installation can enhance the value and appearance of a building. When working on electrical systems, it is important to be aware of the potential hazards and to take precautions to protect yourself and others from harm. Electrical shock can be fatal. Arcing and sparking can cause fires. Explosions can cause serious injuries. Always be aware of the potential hazards and take steps to mitigate the risks. Follow safe work practices. Use common sense. If you are not sure how to do something, ask for help. Safety should always be the top priority. The knowledge of the principles of electricity is important to working safely in a system like this. A grounding system aims to have zero voltage potential. A voltage difference between two conductive objects is what causes the flow of current. Grounding the electrical system is a critical safety measure designed to minimize the risk of electrical shock and prevent damage to equipment. By providing a low-resistance path for fault currents, the grounding system ensures that overcurrent protection devices, such as circuit breakers and fuses, trip quickly to energize the circuit. Also important is that the water pipe itself is electrically continuous. This means that the metal water pipe must be continuous throughout the building to effectively serve as a grounding electrode. Any breaks in the continuity of the water pipe, such as non-metallic sections or insulating couplings, must be bonded around to maintain electrical continuity.